Hello, welcome to this video. This is for Seppo. There's about 5 or 6 questions here. This one is from summer 2017. Summer 17, where is it? Question paper 42, and this is question 2B. Here it is, 2B. Okay, so the reaction between 2-chlorobutane and sodium iodide in propanone is shown. There you go. The rate of reaction can be investigated by measuring something we don't often see in chemistry, but we can investigate it using electrical conductivity. The electrical conductivity changes as the reaction proceeds or progresses due to the precipitation of sodium chloride. All right, this stuff, okay, suggests how the electrical conductivity will change during the reaction and explain your answer. Okay, well, first of all, as you can see on the left-hand side, this is the solvent. This is propanone. Let me get a thicker pen. This is propanone, all right, but you have 3 ions. You have sodium ions and iodide ions in propanone. So if you put electrodes in this solution, these ions will move, all right, to their respective anodes and cathodes. So because these are free to move, this side will conduct, because you have movement of ions, you have mobile ions. But on this side, the ions are locked in the lattice, locked in a solid lattice. And because of that, they won't move. And because if they can't move, so they are immobile. All right. And because they are immobile, charge can't flow. Charge can't flow. And that means there is no current. And that means on this side, it's a non-conductor or poor conductor. And on this side, it will conduct. So as the reaction proceeds, you get more of this non-conducting stuff on the right-hand side. So the electrical conductivity will decrease. Okay, so that's the first answer. How will the electrical conductivity change? It will decrease. Explain your answer. Well, the ions are precipitated out as sodium chloride. Okay, and when they're precipitated out, they cannot move. So conductance decreases. Okay, a nice question. It's kind of an odd one, isn't it? But there you go. All right, let me boost that up a little bit. Describe a suitable method for studying the rate of the reaction. Okay, at 40 degrees C. All right. Now, if we're going to study the rate of this reaction, we've got to take very careful consideration of what they want. It's worth 3 marks. So first of all, they want a temperature at 40. All right. You've got a conductance measurer, or some sort of thing to measure conductance. You've got known solutions. You've got a clock, and you've got everything you'd expect in a laboratory. So the first thing you've got to do is make sure the reactants are, this is what you must ensure. Ensure reactants are at the temperature you're going to do it at, 40 degrees C. Okay. Now they have to be at 40 degrees C at the start. They can't be at the end. They must be at the start when you do the experiment. So what we do is we place reactants or reagents into a water bath at 40 and wait until thermal equilibrium is established. Equilibrium established. Of course, taking ages, isn't it? Now, this is given a special word. We call this equilibrate. Okay, that's to get things at the correct temperature. But you got to start with that. Okay, so that's the first thing you want to do. Number 1 thing. Number 2 thing. Well, you want to add the things together, don't you? But you're conducting a scientific experiment here. So what you've got to do is you have to mix known volumes of the reagents. You don't have to mention how much you're going to add. Okay, it's just an outline, but you have to add known volumes. And when you add the known volumes together at 40 degrees C, you must obviously start the stop clock. Okay, So, I don't know, let's have a look at this. You've got the water bath. Okay, and this is the reaction mixture now. There's my water. There's the reaction mixture. And you're going to put something in there that's connected to your meter, your conductance meter. Okay, so this is at 40, and this is at 40 as well. Okay, and you must start the clock. The clock starts when you add them together. That's important. You've got to say you start the clock when the reactants are mixed. Okay, the clock is started. Okay, well, what do you do now? Well, obviously, you measure as the time goes on, measure the conductance at regular time intervals. Okay. Okay, I don't know, every 30 seconds maybe. I don't know how long the reaction is going to take, but every 30 seconds is fine. You don't know how long it's going to take, but it has to be regular time intervals. All right. And now, obviously, what you've got now is, by the way, this is enough to gain 3 marks. This will give you 3 marks. Each of these points will get a mark. Okay, but now it would be clever. Oh, God, that's not very good, is it? What we're going to do, we're going to do time in seconds or whatever against conductance. Conductance. I think the units of conductance are Simons, but I might be wrong. I don't even know what. I don't even know what the letter for Simons is. I think it's Simons. I might be wrong. Anyway, so at the start, it's going to start. It's going to be high, and as the time goes on, it's going to decrease. So you'd expect the graph to start off high, and it to do something like that. Okay. Now, what you wouldn't know doing this is you wouldn't know. Let's pick this part on your graph. Okay. You wouldn't know. You would know the conductance at this time, X, let's call this, and this is the conductance here. But you wouldn't know the concentration of the reagents here. So I don't know if you're familiar with this. Okay, what you could do is you calibrate the conductance meter, using a calibration curve. Now, this is extra, okay? And what's a calibration curve? A calibration curve is very simply this. You don't do the reaction. What you do is you do on here conductance, and you across here you have concentration. Concentration. All right, and what you do is you start off at a high concentration or a low concentration in this case. So you start off here and the conductance will be low. All right, so there you go. At low concentration, it's going to be 0, and then it's going to go up like this. This is what's called a calibration curve. So you have different concentrations of the reaction mixture, this stuff here. Okay, you have different concentrations of this, of your reaction mixture, and then you draw a calibration curve. And then when you use this graph, you can use the conductance here, and if you know the conductance, you can relate that to a specific concentration. And this is a bit technical, this I agree, but then you can plot a time concentration curve. Okay, if you're confused about this, give me a shout and I'll try and tell you a bit more about it. But the thing I want you to get across this is enough for the 3 marks, just mentioning how you would do it. But then how would you process your results? You need to draw some sort of calibration curve, and that would help you understand how the concentration is changing. You know how the conductance changes, but you don't know what the conductance means in terms of concentration. So we have to plot one of these things, and this is called a calibration curve. Okay. Now these practicals are quite old-fashioned, but you've got to know this stuff anyway because you're a good scientist. So if you have a problem, give me a shout, and I'll talk about this more. Let me stop the video and go to the next one because I think this is going to be quite a long video as it is. Okay, so let me stop this. Okay, this is the second one. I think this is question 6b. Okay, same paper as before. This is aminomethanoic acid or glycine, and it has a pKa of 9.8. Use the zwitterionic structure for aminoethanoic acid in aqueous solutions to write an equation for its dissociation, giving hydrogen ions. Well, Let's first of all draw the amino acid. So it's NH2, CH2, CO2, H. All right. And now I'm going to change this into the zwitterite form. So I'm going to take the proton here and I'm going to put it over here. Okay. So how am I going to do that? Well, I'm going to use a rubber. I'm going to change this to H3. And I'm going to put plus there, and this is minus. So this is the zwitterionic form. And now it's going to lose a proton. So what's it going to look like now? Well, it's going to go back to H2, CH2, CO2 minus, and it's going to lose that proton, H plus. So there it is. There's the zwitterionic form, losing a proton. Okay. Now the next one, we're supposed to find out the pH of a 0.1 molar solution of this, and we got the pKa. So this shouldn't be too hard. The way I do it, because I'm not very good at these things, so I have to start from basic principles. I have to write down what the pKa, what the Ka looks like, and it looks like this. Okay, H plus, all divided by the zwitterionic form, this thing here. Okay, there we go. Now, let's start off with whatever here. Okay, we start off with 0.100 molar here. And how much do we, well, I don't know how much I'm going to get, so I'm going to say X and X. I know it's the same, and the reason they asked for this equation is so you appreciate that for every mole of this guy here, you get 1 mole of hydrogen ions. So it's 1 to 1. So this becomes Ka, which is 10 to the minus 9.87. All right. That's Ka now, isn't it? This is pKa. And this is Ka is equal to x squared divided by 0.1. Okay, so let me do using my calculator. Let me not do this. Let me get rid of that and say x squared is equal to 0.1 times 10 to the minus that. Okay, and this is, I'm going to do this up here, and from that we get x. Let me use the calculator. So it's 0.1 times 10 to the power of minus 9.87. And I get a very, very small number. For x squared, let me put the x squared number. I get 1.35 times 10 to the minus 11. Don't forget 3 sig fig, always. All right, and therefore from that I get x equals, where's the square root button? I'm assuming it's that one, roots equals, oh, obviously I've done that wrong. Let me start again. The root of 1.35 exponential minus 11 is equal to 3.67 times 10 to the minus 6. This is x, which is also the concentration of H plus, isn't it? So from that, if I find the log of this, the minus the log of this, log of that is equal to, it says, 5.43. So I'm going to guess, the pH is 5.43. Now let me cheat. I hate getting things wrong, but it happens sometimes, doesn't it? So let me dig out the answer. What did I say? I think it's 6. Obviously, I haven't got everything ready. 6, and the answer is, 5.4 they want. So we're good there. Okay, I hope that one's clear enough. Let me get rid of this and get the next one on the list. Let me pause the video first. Okay, this is the next one. This is question 6. Let me find out the question paper. The question paper is October, November. Let me write this down somewhere because I know you guys like to know this sort of stuff. It's winter, 17, paper 41, question 6A. Okay, that's the question. All right, again for Sepon. Let me dig around there. First of all, for nitromethylbenzene can be prepared using that mechanism. There you go, looks straightforward. The reaction also forms an isomer as a byproduct. Now, the isomer, this is the 4 position, so the isomer would be, it's the 2 position, isn't it? Okay, because the 2 and the 4 position form at the same time, and the 3,5 if this was electron withdrawing. So you get the 2-4 position there. All right. Write an equation for the reaction between that and that forms the electrophile for the reaction. Now, oh gosh, I'm guessing here. I know it's nitric and sulfuric. I vaguely remember it's 2 sulfurics. I know you get the nitronium ion. You get the hydrogen sulfate. And I think you get the oxonium ion. There you go. Now, there's nothing clever about this. You just got to learn this. All right. I wish there was something clever, but there's not. Okay, just learn it. Night before the exam, just write it out 10 times. Describe how the structure and bonding of the 6-membered ring in intermediate T differs from that in methyl benzene. Oh, that's an interesting question. All right, so we've got some strange things here, haven't we? Obviously, this... Oh, sorry, let me do it. Is it methyl benzene? Yeah. This is sp2 hybridized, isn't it? All right, is that right? Yeah, sp2, and because of that, all of the carbons are trigonal planar, and that's why the benzene ring itself is planar. Okay, because everything is flat now. All right, but in this one we've got sp2, 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 but down here we have an sp3. Okay, because you look at the geometry there, there's 3 bonds coming from that carbon, so it must be sp3. Okay, so the structure and bonding. So first thing I'm going to say is that here, what am I going to say here? I'm going to say in methyl benzene, okay, it's planar. And why is it planar? Because everything's sp2 hybridized. But in T, the bottom carbon is tetrahedral. And why is it tetrahedral? Because it's sp3 hybridized, isn't it? Okay, so there you go. I think that's worth a mark. All right, that's 1 mark. What else can we say? In methyl benzene, even though this is obvious, I think, in methyl benzene, the delocalization is across 6 carbons, but in T, it's only across 5 carbons. Okay, that's one thing we can say. Now, this is a cheap one, but I'm digging things out here. I don't know what else to say. The bond angles. This is, to my mind, the same as this one. But you know what? If you can't think of something, just repeat something in a different way. Bond angles in methyl benzene. Oh, something like that. Methyl benzene are they? They're 60, aren't they? No, they're 120. All of these are 120, aren't they? Because it's sp2. All right. But in T, the bottom carbon is 109.5. Okay. I can't think of anything more than that. All right. What else can we say? I guess there is one thing we can say. We can talk about the number of delocalized electrons. So in this one, there's 6 delocalized electrons. In this one, there's 1, 2, there's 5. Is that right? 5 delocalized electrons, I think. I hope I'm wrong. Sorry, hope I'm right. Well, one of the ones has gone into the bond. No, I guess it's 4, isn't it? So in methyl benzene, and you can check this out. I might be wrong here. There's 6 delocalized electrons. Okay. Now, why is there only 4 here? Well, 2's come out, remember, to grab on. It's not 1 that comes out, it's 2 that comes out. So there's 4 delocalized in T. I hope that makes sense. I know you think, there's only 5 because there's 5 carbons in the delocalized system. But there's only actually 4 electrons because 2 have come out. So this new bond here took 2 electrons away from the ring because it's a proper bond. The nitrogen didn't supply any of those. It's a dated bond from the benzene, and 2 electrons came out. So it starts off with 6, ends up with 4. Hope that makes sense. As always, if you're confused, give me a shout and I'll try and help again. All right, let me stop now. Okay, so this is the next one. This is, let me see, this is summer 18. I've got to hurry up a bit, haven't I? Because this is getting a bit long. Summer 18, 41. I think this is 1C, I think. When sodium oxide reacts with water, an alkaline solution is obtained. Explain why the solution obtained is alkaline. You should use the Bronsted-Lowry. Okay, so what have we got? Sodium oxide is Na2O. We're going to react it with water. Now, we should know this from formula 6 that we get sodium hydroxide. Okay, so it's always good, I think. Is that balanced? Two of those, 1, 2. Yeah, that looks balanced to me. That's good. And sodium hydroxide, the hydroxide ions, can accept protons to form water. Now, these equations are really good. This one we should know, the top one, and this obviously the bottom one we should know. But so first of all, point 1 is sodium hydroxide forms. Okay, and point number 2 is the hydroxide ions can, and now we've got to use the Bronsted-Lowry theory, haven't we? Hydroxide ions accept protons, and so they are basic. Okay, but if you can ever write equations, even though it doesn't ask for them, please do, because they think that's impressive. Okay, so there you go. I'm pretty well sure that's worth 2 marks. Calculate the pH of the solution obtained when 3.1 grams of sodium oxide are added to 400 cc's of water. Right, obviously, let's use this top equation. First thing I want to know is number of moles of sodium oxide. It's 3.1 divided by 2 times 23 is 46. 46 plus 16 is 46. 46, 50 to 62. All right, so the number of moles is that. So this is my calculator. 3.1 divided by 62. Oh, that's an easy one, isn't it? I should have known that. 0.05. So we have 0.05 of this, but we're going to get 0.05 times 2 here, aren't we? So therefore, the number of moles of sodium hydroxide is 0.05 times 2, which is 0.1. Okay, pretty obviously. And therefore, the number of moles of hydroxide ions is also 0.1 moles. Okay, so concentration of the hydroxide ions, which we want to know, is 0.1 divided by 0.4, which is this. Okay, so let me do that. I should know this, but I'm useless at maths. 0.1 divided by 0.4 is equal to 0.25, apparently. 0.25, so that's the concentration. This is this. Okay, so the concentration is 0.25. Well, let me find out the pOH. I'm doing it a cheeky way, aren't I? The pOH is therefore what? It is the log of 0.25, which is 0.6. Okay, I think it is anyway. And then pH is 0.6. So we should know this. The pH plus the pOH is 14. So from this, hopefully, I'm right anyway, we get 13.4. I hope that's the right answer. Let me check. Yep, looks good to me. All right, now there you go. That's how I would have done it. I'd have done this cheeky thing here and done that. All right, so let me do the next one. All right, let me stop the video. Okay, another interesting one. These are 3 chlorides, aren't they? This is a good question. 3 marks, though. It's quite a lot. So let's try and dig into this one. Let me get rid of that, and let me have a look at this. This is, what will be with you in a second. 9. I think 9A, yeah. 9A. Where are we? Yeah, we're 9A. And this is summer 19. Question, paper 41. And this is 9A. We've got 3 chlorides here. Explain the relative hydrolysis rates of hydrolysis. Okay, so what does hydrolysis mean? It takes away this, sticks an OH on. Okay, basically it hydrolyzes the water. That's why it's called a hydrolysis. And we get HCl as well. Now we can test this, the speed of this, if we have silver ions in solution and we introduce those using silver nitrate, and you get a precipitate. Okay, and the one that gives the fastest precipitate is going to be the one that hydrolyzes the quickest. So first of all, let's classify these. Well, this is called an alkyl chloride. This is an acyl chloride, and this is an aryl chloride. Okay, so let's draw them all down here. Cl, these are H's. This is my alkyl chloride. Let's do my acyl chloride. And let's do my aryl chloride. Okay, so basically the strength of this bond determines which one's going to be the first to go. All right. Now this is going to be the most easily to hydrolyze. So let's do this. This is going to be number one, the fastest, the quickest. This is number two, and this is number three. Okay. Now the reason this is going to be quick is because this is delta negative. The chlorine is delta. The oxygen is also delta negative. Therefore, the carbon in the middle is very, very delta positive, and it's going to be attacked very easily by the hydroxide ion. Okay, it's going to attack that very easily. All right. So number one is that, and the reason I would give is because the carbon. Let's do it in a nice color. For number one, I'm going to call it the acyl. Okay, the carbon is very delta positive, easily attacked. Oh, I just got attacked. That looks good enough by the OH fast hydrolysis. Okay, let's have a look at number two. Number two is the alkyl. Okay, this one here. Well, there is a delta plus and delta minus, but this one is next to only the chlorine, so it is delta positive, but less so than above. So it will get attacked, but it will be slower. Now the aryl, this one here. Well, let's try and draw it a little bit nicely. If you think of these are the p orbitals coming out, and there's the chlorine. Chlorine has its own p orbitals. Now this is the delocalized ring, as you know. Okay, and these get sucked into the ring. These electrons on the chlorine. Okay, now I'm looking at the answer scheme here. Do they say it nicer? Yeah, they say the bond. I'm reading straight from the answers because sometimes you need their briefness. I think the bond is part of the localized system. Okay, that's a nice way of putting it. I think. Anyone else? Or you could say for this one, the p orbitals. This is what I'd be more inclined to say. I think the p orbitals on the chlorine overlap with the pi system. Okay. Now, what does that mean? It means this bond here shortens. Okay, and if it shortens, it strengthens. So this one is the hardest to hydrolyze. This one, in fact, does not hydrolyze. All right, because the C-Cl bond shortens for the reasons below. Shortens and strengthens. Okay, it's a good question. A very nice question. So well done, Sepal, for asking that one. Any problems, please ask. Let me post this now because I think this has gone on for long enough, I'm afraid. All right, bye-bye.